Okay. So we started chapter number 6. We started chapter number 6, and that was Introduction to Convection. And what we did was that we studied in the convection, the most important thing, or the very first concept, is of the boundary layer. So we studied the boundary layer concept about the velocity boundary layer, thermal boundary layer, things like that. Okay, and these are some of the very essential and very important concepts for in the beginning of the convection portion. Then we studied about the heat transfer coefficient. Okay, and I told you that there is a local heat transfer coefficient. So heat transfer coefficient varies along the length of the plate, and this variation is because we have a boundary layer thickness varying. Okay, and that's why heat transfer coefficient vary. And then we will have an average heat transfer coefficient. Okay, and we can develop a relationship between average and the local heat transfer coefficient. These are the things that we actually studied last time. Okay, so now let's move ahead, and we have a numerical related to it. Okay, so let's solve a numerical. So you remember that we said that the average heat transfer coefficient is 1 upon L integral Hx dx, right? So if we know that what is a function of h as a what is h as a function of x, how is the local heat transfer coefficient varying with x? If we integrate it over the entire length, we can find out the average heat transfer coefficient. Okay. So now this is example 6.4. It's a very important example because it will also develop a fundamental and the basis for some other concepts that you're going to study after this example. Okay. So let's go through with this example. Water flows at a velocity u infinity 1 meter per second. So that means it's a free stream, but that's water. Water is flowing at this speed. Free stream velocity of water is u infinity equals to 1 meter per second. I told you we will call it sometime v, sometime we call it u. Okay. Over a flat plate of length L. So now we have a flat plate. Okay, and this water flows over the flat plate. And what's the length of the flat plate? L equals to 0.6 meter. Okay, that's the length of the flat plate. Consider two cases. Now we have to consider two cases. One for which the water temperature is approximately 300 Kelvin. So in the first case, water temperature is approximately 300 Kelvin. Okay. So case 1, T infinity is 300 Kelvin. Okay. And the other for an approximate water temperature of 350 Kelvin. So what's the difference between the two cases? In one case temperature is 300 Kelvin, in the other case temperature is 350 Kelvin. The only change in between the two cases is the temperature change. Okay, so case 2, T infinity equals to 350 Kelvin. Okay. In the laminar and turbulent regions, experimental measurements show that the local convection coefficients are well described by these formulas. So now you know that when the flow passes over the plate, we will start with the laminar region, and then we move towards the transition and then the turbulent region, right? So this is how the flow occurs over the plate. Okay. So it starts with the laminar, and then we have the turbulent. Okay. For the laminar region, the heat transfer coefficient is governed by this equation. For the laminar region. Okay, C, which is a constant for laminar case, x raised to the power negative 0.5. For the turbulent case, if the flow becomes turbulent, for the turbulent case, H is equals to C turbulent x raised to the power negative 0.2. Okay. Now what are the values of these constants? The values of these constants depend upon the temperature. We had two cases, case 1 300 Kelvin. So if it is 300 Kelvin, the value for C is this for laminars, this for turbulent. If it is 350 Kelvin, value of C is this for laminar, this for turbulent. Is it clear? Okay. As is evident The constant C depends on the nature of the flow as well as the water temperature. So the value of C actually depends upon two things. First of all, what is the nature of the flow? Is it laminar or is it turbulent? Secondly, even if it is laminar, then it depends upon temperature, what temperature it is. Okay? So value of C depends upon the nature of flow as well as the water temperature because of the thermal dependence of various properties of the fluid. Okay? Determine the average convection coefficient. Average heat transfer coefficient, convective heat transfer coefficient. So we need to determine H average. This is what we need to determine, H average. Okay? Over the entire plate, over the complete plate. So, okay, for the two water temperatures. Now we have two cases. We need to find it for both the cases. Okay? So formula is very simple. Formula is that we have H is equals to 1 upon L. L is known, right, over the entire plate. Okay, okay, so it's 0.6. Okay, the integral Hx dx. Now is a problem. Which H should I use? I have a formula for Hx this. I have a formula for Hx this. If I use here turbulent, that means I'm assuming that everything is turbulent. If I use laminar, then I'm assuming everything is laminar. Even if I add them together, I'm assuming that there is laminar and turbulent. We don't know. Do we have a turbulent portion here or not? Now, how do we determine whether the flow becomes turbulent or not throughout the length of this plate? Is through the critical Reynolds number. We know that if the Reynolds number becomes greater than 5 into 10 to the power 5, then it will become turbulent. If it is less than 5 into 10 to the power 5, it remains laminar. Okay. So what we do is that now we use the formula for critical Reynolds number, which is equals to rho VL upon mu. Okay, rho VL upon mu, and critical Reynolds number is how much? It is 5 into 10 to the power 5. So if this is the critical Reynolds number, okay, we need to know after how much length the Reynolds number becomes critical Reynolds number. So that means we will know that after how much length the plate would become turbulent, the flow over the plate become turbulent. Before it, the flow was laminar. We know it starts laminar, but we don't know that after how much length it would become turbulent. Okay, so this, by using the critical Reynolds number, we can find it. Okay, now the thing is that we have the velocity. Velocity is a free stream velocity, which is known. Okay, which is fixed. Okay, length we need to find out. This is the distance we are finding when the flow converts from laminar to turbulent. So we know exact length after which it will become turbulent. Okay, so that's what we need to find. Velocity is known. Now there are two parameters here, density and viscosity. You get it from the tables, but you need temperature. Now we have temperature, but we have temperature for two cases, so we will get it separately for two cases. Okay, so we will get two length for two cases. Okay, so we will put density for water. This is water, right? Water flows at a velocity. This is, we will put density for water, we put viscosity for water at 300 Kelvin, okay, and we will get what is the length after which flow become turbulent. Similarly, then we will put for case 2 density of water, viscosity of water. We will again get a length, and we will determine that what is the length after which it becomes turbulent. Okay. So for case 1 and case 2, they solve it for 2 times. So L critical, let's call it L critical. So once I solve it, so L critical, or here put it X, it's the same thing. So X critical comes out to be 0.43 meter for case 1. Okay, 0.43 meter. 0.43 meter means for the case 1, from length 0 to 0.43, it would become it would remain laminar, and after 0.43 it becomes turbulent. Okay, so suppose 0.43 is somewhere here. This is 0.43. So in this region it remains laminar, and then it becomes turbulent. So that means over the entire plate, it is a combination of laminar and turbulent for case 1. Okay. Suppose if the length comes out to be 0.7 here, what do you think? The flow remains laminar, or it remains turbulent, or what would be the case? If after putting values answer comes 0.7, suppose. That means your complete length is 0.6, and the critical occurs at 0.7, means over the entire length range it remains laminar, never goes turbulent. Okay. Suppose, it's not going to happen, but suppose L critical comes 0. All the flow becomes turbulent. The L critical determines what kind of flow will be there in which region of the plate. Is it clear?
Yeah, but how did we know that it is laminar?
How we know it is laminar? It is very clear, because Reynolds critical, Reynolds number here for this fluid, density is not changing, viscosity is not changing, velocity is not changing. Only the thing which is changing is the length traveled over the plate. So it will always start laminar. It will always start laminar, but after this critical Reynolds number has reached, it will become turbulent. Okay. So by putting the value of critical Reynolds number, we know exactly at what position it converts from laminar to turbulent. I told you, now for calculation purposes, transition region is not there. We don't consider it. We consider either laminar or turbulent. Okay. So there is a very fixed line, there is a very fixed point after which it becomes from laminar to turbulent, and that fixed point is 5 × 10⁵ Reynolds number.
Yeah, but I mean we have different temperature, 2 cases.
Okay. Other case we have not yet solved.
Oh,
okay. So now we put the values for the other case. For the other case, density and viscosity will change. Other things would remain same. Okay. So once you put the values for the other case, you find out that the critical Reynolds number is 0.19. So 0.19 means, suppose 0.19 is somewhere here. So in this region you have laminar, in this region you have turbulent. So both the cases we have laminar and turbulent flow present over the entire plate. Is it clear? Till this step, is it clear or not? Is there anything which is not clear? You can ask.
The big value.
Big value, which big value?
0.43 and 0.19. So the big value
No. The big value, small value, don't consider the value big or small like this. There are 2 separate cases. For first case, it is 0.43. That means for 0.43 meter, it was laminar. From 0 to 0.43, it was laminar, then becomes turbulent. Case 1 complete. Case 2 separate case. Now again water is flowing, but this time water is at 350 Kelvin. Okay. So in case 2, for 0.19 meter it remains laminar, after that it is turbulent. Is it clear? There are 2 separate cases, don't mix them up. Okay. It's like solving problem 2 times. Is it clear till this point or not? If it is clear till this point, now we know what is the region of laminar and what is the region of turbulent. So we can divide our integral into 2 parts. Okay, we can divide this integral was from length 0 to L, complete 0 to 0.6. But for 0 to 0.6, we cannot put the complete one value of H, because H is different for laminar, different for turbulent. So now we can divide it. Okay, so this thing have to be divided. Okay, so now what we do is that we do it divided like this. First we make it from length 0 to L critical. L critical. Okay, first we make it from 0 to L critical, And in this case, if we make it from 0 to L critical, now we know the formula for the laminar case. C laminar x negative 0.5. C laminar x negative 0.5, okay, dx plus, yes, now L critical to complete L, okay. And now we put C turbulent x raised to the power negative 0.2 dx. Is it clear? So now we know the ranges. Okay, when we are solving for 300 degrees centigrade, then we put the C values for 300 degrees centigrade. When we are solving for 350 Kelvin, then we put the C values for the 350 Kelvin. Is it clear? And we solve it. Then the solution is simple. Okay, so after solving, putting the values and solving, okay, we get that the value of H for the first case comes out to be 1620. Value of H for the second case comes out to be 3710. Is it clear? Do you understand the problem solution or not? Okay. Suppose L critical came out to be 0.7 meter. Okay. Suppose L critical come out to be 0.7 meter. How would you apply this formula there?
0 to L.
It will be only 0 to L, because L critical is outside the length. So it will be only 0 to L, just laminar, no turbulent portion. Is okay? It's a good question actually. Is there anything that you do not understand?
So if you do like this 0.7, you mean 0 to L, the boundary for that, okay. But for the case 1, it was still 2 parts.
Then it will be 0 to L, and L is 0.6. When you try to find the properties of water, finding density would be interesting. You have the property table with you? Can you find the density of water at 300 Kelvin or 350 Kelvin?
I think it was the density of water not steady. It was 1000 every time.
It's a function of temperature. Temperature here is 300 Kelvin. It's written here, use table A6.
Because how can we know this table A6? Because sometimes take it from table A1 because it's half or half.
You have to go through the tables to know which one to use. Tell me the density of table A6, huh? Tell me the density of water at 300 Kelvin. Interesting, huh? Ah, interesting.
Because V volume F, I think, divided by 10. That's the volume?
Specific volume. Because what is the relationship between specific volume and density? Density is mass per unit volume. Specific volume is volume per unit mass. So you get the value of mu and take it minus power minus 1, 1 upon. You see here, it's written here. I told you the tables are good, but you need to go through it to know how they are written, what values you need to take. Okay? Sometimes it goes very interesting. This happened with the students when I was taking their first exam. They did not go through the table, and on that day of the exam they have to put the density, and everybody was calling, "Doctor, please, there is no density here." Okay. Do you see the units of C here? Units of C. Does it make sense to you? Units of constant C. Does it make sense to you? Yes. It has to match here with the formula such that the convection unit becomes watt per meter square Kelvin. Since you have x here negative 0.5, x here negative 0.2, that's why unit of C will be like this. Okay. This is actually not heat and mass transfer.
Can we go back to the properties of this equation? We have mu. Discuss it here. Discuss. It's written that's multiplied by 10 to the power 6. And here's multiplied by power 10 to the power minus 6.
This is one another thing I wanted you to go through the tables. This is because I told you in one of the lecture that there is a problem in the units written. It's not problem, it's correct. What it says is that, now look here, what it says is that mu into 10 power 6 is equals to 855, right?
Yes.
So that means mu is equals to 855 into 10 power minus 6.
Get mu, it's
Do you get it?
So for the specific volume for the fluid, it's the same.
Same. This is how units are given there in the book, okay? The question in chapter number 2, where the only object is to take values from the table, you will counter all these problems when you actually try to solve yourself taking values from the table. You will counter these problems. And that is the reason why that question is there, so that you get used to how to read the tables here. Okay? So let's move ahead. Now there are certain there is certain theory about the boundary layer equation. Okay, now this is a theory that's not really related to heat and mass transfer. It's more related to fluid mechanics, and probably you will go through it in the course of the fluid mechanics. So we have the two-dimensional Navier-Stokes equation. Okay, what we do is that whenever we have the fluid flowing, we develop the mass conservation or continuity equation. It's like this. So you will go through this in fluid mechanics. Then you have the momentum conservation equations. Okay, x momentum conservation, y momentum conservation. Probably you will go through it in the fluid mechanics as well. Okay, and then you have the energy conservation equation. Okay, among the energy conservation equation, these are the viscous dissipation terms. Okay. Anyways, what we do is that we develop the boundary. Okay, these are the general equations for any fluid flowing. Okay, these are the general equations for any fluid flowing. These are all the energy balance, momentum balance, mass balance equations. Okay, so this is the mass balance, this is the momentum balance, is basically the and the last one is the energy balance equation. However, when we want to solve it within the boundary layer, we apply the boundary layer approximation. What boundary layer approximation means, because these equations, in order to solve for these equations, it's quite complicated. Okay, these are very complicated equations. So we try to simplify them. For simplification, what we try to do is that we make some approximation that will cancel some of the terms. And probably you will go through it in more detail in the course of fluid mechanics. So what are these approximations? Within the boundary layer, we can assume that u is a function of x, not y. And that makes sense. If you have a body and the fluid is flowing across the body, so you have a boundary layer developed here, okay? And within the boundary layer, we discussed that there is velocity gradient from the surface to the boundary layer, but this is only in this direction, vertical. So if I call this x direction, this is y direction. So velocity is only varying in y direction. There is no velocity variation in x direction. Okay, so within the boundary layer, it's only varying in y direction. Yeah, there might be a little velocity variation in x direction, but that is very small. Larger velocity variation is in the y direction. This is one of the approximations, so we will cancel some of the term. Wherever we have velocity variation in x direction, we will cancel that because it's too small. Then we have the flow is flowing from right to left, okay, from this end to that end. So flow occurs because of the pressure difference. So that means is we have high pressure here, we have low pressure here, the flow is flowing in this direction. There is no flow in the up or down direction. So that means there is no pressure difference in the y direction. So although there will be slight pressure difference in the y direction, but that's negligible. So that's another approximation. Okay, so we have only, so basically dava p by dava x becomes actually dp by dx because it's only varying in the x direction. Okay, and similarly we have for the temperature these approximations. So what happened is that when you put these approximations, so our boundary layer equations, which were so complicated equations, many of the term cancels. Okay, so our equations become simplified. However, these simplified equations still need to be solved, okay, and they are solved analytically. I'm not going to go through the solution. You're going to go through this solution in detail in the course of fluid mechanics. So anyways, we're going to go towards the end results, okay. So the end result is that we apply the similar, okay, these are the simplified equations, okay. And then after that, we apply the boundary layer similarity. Similarity is a concept that you will be introduced in the fluid mechanics course as well. And it's one of the most important concept and widely used in the industry. It has a lot of applications. So concept of similarity is that we don't want to use the terminologies with units. We want to develop the dimensionless terminologies, okay? And dimensionless terminologies have an advantage. If you have a dimensionless terminology, it becomes independent of any fluid property and things like that. Now it could be applied generally to anything, okay? That's, for example, now it's the Reynolds number. Whether a flow is smooth or the flow is not smooth, it does not matter what the fluid is. It does not matter what is the velocity of the fluid. It does not matter what's the density of the fluid. It does not matter what's the viscosity of the fluid. It does not matter how long the fluid has traveled, because you know it's actually just the Reynolds number which you have to focus. Whether it's honey, whether it's water, whether it's alcohol, whether it's blood, whether it's whatever it is, any fluid. If you just know that the Reynolds number is below this number, then we know that it's laminar, it's smooth flow. If it is above this number, we know that it is not smooth flow. So it becomes independent of all these parameters, okay? So by the similarity, we develop these kind of dimensionless parameters, which helps us analyze problems in a much better way. We're independent of fluid properties, things like that. The principle of similarity is based on determining similarity parameters. These are the similarity parameters, Reynolds number. is a similarity parameter. Before Reynolds number, you studied some other numbers, Biot number. So it's a ratio number, okay? It does not depend upon anything, no unit is there, Fourier number. These are all the similarity parameters, okay? That facilitate application of results obtained from a surface experiencing one set of conditions to geometrically similar surfaces experiencing different conditions. So once you have the similarity developed, then you can apply the case of one condition to the other condition to some other problem, this similar kind of things. Okay. So we apply the similarity. For similarity, as you know, we have to put everything non-dimensional. Even if you have a length x, we don't put it x. We put it x star, which is x upon L, dimensionless. If we want to put temperature, we don't put, we put theta star. So it's T minus T infinity upon Ti or Ts minus T infinity. Okay, everything in dimensionless form. There should be no dimension throughout within it, with anything. Okay, so we put everything in the dimensionless forms, and we apply the Buckingham pi theorem. I don't know if you have gone through that Buckingham pi theorem.
Yeah, I think.
Yeah, fluid, yes. So we apply the Buckingham pi theorem. It's a mathematical theorem. We go through it. We come up with yes. We end up into the final similarity functions. So once we go through it, we end up with some of the similarity functions here as mentioned. Okay. So what we come across Reynolds number, where Reynolds number is a dimensionless parameter that you have already studied, okay? But it comes out after this similarity analysis, okay? And what does Reynolds number means? Reynolds number is a ratio of two forces, inertia force over the viscous force. Rho VL is the inertia force. Mu is the viscosity, that's a viscous force, okay? So it's basically what? In physical terms, Reynolds number means what? We have the inertia force. Inertia force tends to make a fluid keep on continue moving forward. Viscous force, it's resistance between layers, it tends to stop the fluid. So there are two forces fighting. One force is trying to make the fluid move forward, other force fighting to stop the fluid motion, okay? So if the inertia forces is high, the fluid is still be moving very quick. If the viscous forces are high, then the fluid will be moving slow. Okay, and that determines the smoothness of the fluid flow. Is it clear? Then we have another terminology, which is the Prandtl number. What's a Prandtl number? Prandtl number has a formula. Prandtl number has a formula Cp mu upon K, or it could be written as mu upon alpha. Now how does Cp mu upon K equals to mu upon alpha? I will keep it for the short questions in the final exams, right? So this you can do it yourself if you can do it. Okay. So anyways, Prandtl number is Cp mu upon K, or could be written as mu upon alpha. What is mu? Here the mu is dynamic viscosity. Kinematic viscosity. Kinematic viscosity, and this is alpha is thermal diffusivity. Okay, we studied alpha in chapter number 1. Okay, and we talked that its unit is meter square per second. It's thermal diffusivity. Okay, and we call this as momentum diffusivity. Okay, and its unit is also meter square per second. So basically meter square per second meter, it's also dimensionless quantity, Prandtl number. Okay, so Prandtl number says what? This is the momentum diffusivity, this is the thermal diffusivity. Suppose if I have a bowl of water, and I have the bowl of water is at 20 degrees centigrade, and I have a pen of 100 degrees centigrade, or I have something. I drop it in between, in the center. Okay, so what will happen? There will be wave propagated, dissipated. So, okay, as well as since the temperature here was high compared to the bowl of water, so there will be heat dissipated. Now it's a race, which one goes faster? Okay, so if both are equally fast, the wave is equally propagating with an equal speed as compared to the speed of the heat propagation, then Prandtl number is 1. Okay, so momentum dissipation is the same as thermal dissipation. Okay. However, if suppose that the wave propagated very quickly, but the heat dissipation is slow, okay, so then Prandtl number will be greater than 1. Okay. So suppose we have liquid mercury. In case of liquid mercury, it's a metal. it's a metal, so thermal diffusivity will be very quick. It's very high. Okay. However, it's very thick. It's very dense, very heavy. So momentum diffusivity will be slow. Okay. So in that case, your momentum diffusivity will be less, and the thermal diffusivity will be high. So Prandtl number will be less than 1. So Prandtl number it's a ratio of how quickly the momentum diffusivity occurs compared to how quickly the thermal diffusivity occur within the fluid. Okay. So it's a ratio of 2 diffusivities. Reynolds number is the ratio of 2 forces. Biot number is the ratio of 2 resistances. Fourier numbers is the ratio of 2 heat energies, energy conducted over energy stored per unit time. Okay. Which parameter is the ratio of what thing is important for short questions point of view? I will repeat again. Reynolds number is a ratio of, Reynolds number is 2 forces, inertia force over viscous force. Prandtl number is a ratio of 2 diffusivities. Biot number is a ratio of 2 resistances. Fourier number is a ratio of 2 energies. So what number in physical terms is a ratio of 2 things is something which is important for short questions point of view, because that's a physical understanding. Okay. What is the importance of that number? Okay. It has a formula, this is other thing. But other than the formula, what physically, why does we have that number? What is this number physically telling us? This is also important for your understanding. Is it clear? So we have the Prandtl number here. Now Prandtl number is a property you will have here for all the tables. Okay, for all the tables, if you see your appendix in the tables where you have all the properties, one of the property Prandtl number is also given. So it changes with temperature. Okay, it depends upon temperature. It's a hugely dependent upon temperature property. Change the temperature, Prandtl number will change. Okay. Is there anything so far that you do not understand? These are some of the concepts here. In chapter number 6, there are a lot of concepts that we are going to discuss. But these concepts are very important for the future chapters, for the next chapters that you are going to go through. Okay. This portion, very, very important. Okay. Gives you the physical significance of these numbers. So don't disregard or this slide completely itself, because this discussion is also important. Okay, go through it yourself. Okay. This is about the importance of Reynolds number and Prandtl number. Okay. Okay, this table is not important for the heat and mass transfer case. It's important for the fluid mechanics. Okay, so it's also not there in the book of tables video. Now there is one thing. Let's come back to the problem that we just solved before. If you remember in that problem, what was the thing? We wanted to find the heat transfer coefficient, and we know that heat transfer coefficient had a different formula for the laminar case, had a different formula for turbulent case. So that means our heat transfer coefficient is a function of, how do we determine if the flow is laminar or turbulent? Reynolds number. So it's a function of Reynolds number, right? So you change the Reynolds number, the heat transfer coefficient would change. The other thing, there was another parameter based on which the formula was changing, and that was the temperature. So we had different formulas, but within the formulas it was dependent upon temperature. So if we have different temperatures, we had different values of C, right? So we have T here as well. Temperature is also important for the heat transfer coefficient. Now the thing is that for temperature, we can use the Prandtl number, because Prandtl number is hugely dependent upon temperature. So if temperature vary, Prandtl number vary. So basically, heat transfer coefficient depends upon Reynolds number and the Prandtl number. Okay? Prandtl number. Now, this is a dimensionless quantity, Reynolds number. This is also dimensionless. H is not dimensionless, and we don't like it. We want to put everything dimensionless. So H has a dimension. And what's the dimension of H? It is watt per meter square Kelvin. Now we need a number which can represent H, but it is dimensionless. We need a number which could represent H, but it should be dimensionless. Okay? So for that, we represent here a new number. We call it Nusselt number. N-U-S-S-E-L-T. Nusselt number. Okay? Nusselt number is determined as HL upon K. Nusselt number is determined as HL upon K, right? Now, if you put the units of H and L and K, you will find out that now it is a dimensionless number. However, I need to ask you at this point one thing. Have you seen this formula before?
Yeah.
Where?
For the point.
Exactly. Now there is a problem here. How come two numbers have the same formula? Byte number has the formula HL upon K. Nusselt number again has the formula HL upon K. But they are two different numbers of two different ratios. There is a big difference. There is a big difference. The difference is that in case of byte number, H is convection coefficient, clear. L is the characteristic length. What is K? K is thermal conductivity of the material. Okay, of the solid body. Here, H is of the liquid. L is the length across which the liquid has traveled. K is not of solid body. K is also of liquid. That's the difference. Both are HL upon K. In case of byte number, K is of solid. In case of Nusselt number, K is of liquid. Now this is a very small difference, but this is the area where students do a lot of mistakes. They forget that K for the Nusselt number was not for solid, it was for liquid, and they put the K value of the solid. In case of byte number, sometimes they confuse it other way around. In case of byte number, instead of putting the K of solid, they put the K of liquid. Okay? So it's KF, fluid. KF. Is it clear? Same formula, HL upon K. But K is not of solid. Here K is of liquid.
Even in the byte number, H will be for solid.
No, H here, because H is between solid-liquid interface. So it's going to be there same. There is no problem in H. The problem is only in the K. Okay? Problem is there only in the K. Okay? Is it clear? So now we have a new number, Nusselt number, which is HL upon K and can be considered as a dimensionless heat transfer coefficient. So now it makes sense, instead of putting H, or put here Nusselt number. Okay? And now it is dimensionless. Okay? But you remember one thing, if we have H, there are two possibilities for H. H could be local, H could be average. If H is average, then it does not depend upon the location. If H is local, then H varies with X. So if I say here that N is average, then it's a function of Reynolds number and Prandtl number only. But if I say here NU is local, then it's a function of X, which is the location, and the Reynolds number and the Prandtl number. Is it clear? Because H varies with X. So similarly, Nusselt number would vary with x, because at Nusselt number is a dimensionless heat transfer coefficient. Okay.
So do we put X or X star?
I'll put here x star. Good catch. Because we need to put everything dimensionless. We hate dimensions. See? Okay, so there is a question here. Go through the solution yourself.
Me too.
These kind of questions are very good to put here, because students feel that the solution is not there in the slide, so doctor will ignore it. Okay, so it's a simple problem. Just go through it yourself. Okay, so now we have the last problem for this chapter. After this problem, chapter number 6 is over. Do you need a break of some time? Okay, let's have a break of some time and then we'll continue. Anyway, so far, is everything conceptually clear or not? Okay, I know things are heavy and they are, I know, accumulating one over the other, but I want it to remain okay conceptually. Okay, let's come back to our lecture. So now this is a problem of a similarity analysis, a similar kind of problem that you are going to solve in the fluid mechanics as well. Okay. Consider convective cooling of a two-dimensional streamlined strut of characteristic length L equals to 40 millimeter. This is statement. How much of this statement do you understand? Consider convective cooling. Convective cooling means by using convection heat transfer cooling of a two-dimensional streamlined strut. What is a streamlined strut?
Maybe static or unstatic.
This is a concept of fluid mechanics. You will study that in that course. However, let me explain you as a bit of gist. You see, you have a plate here, okay, and suppose a fluid is flowing. So what happens is that how would the fluid flow would be? It would be like this, right? So you have boundary layer region developed, okay. Now the boundary layer region presents some resistance, okay. So if you want to eliminate it, we can reshape the object from flat to like this, okay. So that the fluid flow, the object is redesigned in the shape of the fluid flow that will go across the object, okay. So it was a plane surface. We can redesign it in the form of the main stream of fluid, the way it will flow, okay. If we do it like this, if we stop at this point, so then you will have wake region here, okay, and the wake region produces another resistance to the flow, okay. So we need to eliminate the wake region, so we don't want the fluid to get separated out, okay. So we design the object such that the fluid remains in contact with the object until it goes off. So our flat plate, which was initially flat plate, when it's streamlined, its shape becomes this, okay. So now it is a streamlined thing, okay. Most of the time you'll see that when you have the bullet train in China, in Japan, or you have a very speed car, racing car, everything is made streamlined, keeping into consideration how the air will flow across it, okay. so that you make the object in the shape that it does not pose any resistance to the flow of air. It will go rightly within the air quickly. Okay, that's why the wings of the plane, wing has to move like this. So that's why the wing of the plane is made streamlined of this shape. Okay, so that's how the wings of the plane is made. So they move in the air such that the design is made such that they pose minimum resistance to the air. Okay, so that's the streamline. That's why I said two-dimensional. Two-dimensional means now this shape is there on a plane, 2 dimension. Third dimension is the length, but the cross section is the same throughout length. Okay, so on a plane it's a 2-dimensional streamlined strut. Strut is anything which is which has certain length. Okay, of characteristic length 40 millimeters. So the length here from leading edge to the trailing edge, that's the characteristic length here, is 40 millimeter. Okay, so consider convective cooling of a 2-dimensional streamlined strut of characteristic length 40 millimeter. The strut is exposed to hydrogen flowing. Now what is the thing which is flowing here? It's hydrogen. Hydrogen flowing, and hydrogen is at 2 atmospheric pressure. There's also 1 atmospheric pressure is the normal pressure we are living in. 2 atmospheric pressure means pressurized. Yeah. So it's pressurized hydrogen. Velocity is 8.1 meter per second, and the temperature is, what's the temperature? Negative 30 degrees centigrade. Wow, negative 30 degrees centigrade. That's the temperature of hydrogen. Okay. Of interest is the value of average heat transfer coefficient. Now this is our interest. We want to find the average heat transfer coefficient. So we have a strut which is in hydrogen, pressurized hydrogen at negative 30 degree, and we want to find out how much is the heat transfer coefficient from this strut. What is the average heat transfer coefficient from the strut? Okay, when the surface temperature is negative 15 degrees centigrade. So the strut is at negative 15 degrees centigrade, the hydrogen is at negative 30 degrees centigrade. Obviously hydrogen is at lower temperature than the strut, so some of the heat from the strut will be rejected out, and when the heat is rejected out, we need to find out the average heat transfer coefficient. Now how can we determine the average heat transfer coefficient? One way is that we make a room, a very pressurized room. We do not fill it with air, we fill it completely with hydrogen. We cool the hydrogen to negative 30 degrees centigrade. So obviously when you cool the hydrogen to negative 30 degrees centigrade, that means you need a room very well insulated. Okay, and then you put the strut into it and make the air to flow, not the air, make the hydrogen, pressurized hydrogen to flow, and perform the experiment, and you get the experimental results. You can get it, cost you a lot of money. Okay, will cost you a lot of money to generate this environment. So here engineers want to do this, they want this value, okay, but they want to move in a smart way. They want to move in a smart way, don't want to conduct expensive experiments. Okay. So rather than conductive expensive experiments involving pressurized hydrogen, an engineer proposes to take advantage of similarity. Now we have an engineer who wants to take the advantage of similarity, okay, by performing wind tunnel experiments. So we have wind tunnel. Wind tunnel is what? It's like a small room where the wind can blow. Okay, so he wants to use the wind tunnel experiments to find out whatever he wants to find out, the convective heat transfer coefficient for this case. Now what is the thing? Instead of hydrogen, now he wants to use air, regular air for the experiment. Instead of pressurized hydrogen, he wants to use the air at the normal pressure. Okay. So, rather than conducting expensive experiments involving pressurized hydrogen, an engineer proposes to take advantage of similarity by performing wind tunnel experiments using air at atmospheric pressure. Air is at 23 degrees centigrade. You don't want to put the air at minus 30, 23 degrees centigrade. A geometrically similar strut of characteristic length 60 millimeter. So, he had a model strut for experiment, and that strut is basically 60 millimeter length, okay, and parameter 150 millimeters placed in the wind tunnel. Okay, so now he wants to find H. Okay, so you have two cases. One case is of hydrogen, the other case is your experiment. So that's the actual, that's the experiment. Okay. In the actual, you have hydrogen. In the actual, temperature is minus 30 degrees centigrade. Okay. In the actual, pressure is 2 atmosphere. But he don't want to use these conditions. We want to use, and what we want? We want H bar, average heat transfer coefficient for this case, hydrogen case. This is what we want to find out. Okay, when the surface temperature here is minus 15 degrees centigrade. Now he want to find this thing, but he don't want to use these conditions. He want to use the condition of the experiments, where in his experiment he is doing it in a wind tunnel. So it's not hydrogen, it's actually air. Okay. And its temperature is not negative 30 degree, its temperature is normal ambient air temperature 23 degrees centigrade. Okay. And its pressure is not 2 atmosphere, its pressure is 1 atmosphere. Okay. He want to use these conditions and find this H. Is it clear? Do you understand the problem statement here? Okay. Now, based on similarity, you can find this, because this is a function of Nusselt number. So if we find Nusselt number, we will find this. Okay. So Nusselt number for the case of hydrogen will be, if this is equals to the Nusselt number for the case of air. Okay. If the Nusselt number for the case of hydrogen is equals to the Nusselt number for the case of air, then we can find, then whatever the H we will get from here, we will use it to get H from here. Okay. So we need to make the Nusselt number for the two cases equal. If we make the Nusselt number for the two cases equal, then we can apply similarity, find out H for this case. Okay. Now, in order to make the Nusselt number for the two cases equal, since we want average, okay, so here let me put here average. So average Nusselt number depends upon Reynolds number and Prandtl number. So we need to make sure that the Prandtl number and Reynolds number for the two cases are same. If we know that the Prandtl number and Reynolds number for the two cases are same, then the Nusselt number of the two cases will also be same. Okay. Now let's talk about Prandtl number first. Prandtl number for hydrogen case and Prandtl number for air case. Okay. So if we use the properties of the table, if we see the Prandtl number I told you is given in the appendix against the properties. Okay. So for air, the as per the properties given, the Prandtl number is 0.707. Okay. For air, okay, what temperature you will use? What temperature you look for example here the temperature that you will use will be the average of the two. Similarly, the temperature here you will use should be the average of the two. Here it's given that what is the temperature of the 30. Temperature of the surface here is 30. So here Ts is 30. So you take the average of 30 and 23 for here, and average of minus 15 and minus 30 for hydrogen. Okay. So if we try to find out the Prandtl number for air, on the average temperature, it's approximately 0.707. And if you want to find the Prandtl number for hydrogen, table A4, okay, at the average temperature, it's again 0.707.
Here is 0.720.
0.720, which temperature you are using?
250.
250 Kelvin.
Yeah.
Sure. This is for air. See? One used for hydrogen. One case is of hydrogen, other case is for air. Okay? So it's 0.707. So one thing is very clear. The Prandtl number for this case is Prandtl number for this case. It's justified. Okay? Now let's move ahead. Now if we make the two Reynolds numbers same, then we can apply this. Okay? Now the Reynolds number for hydrogen case and Reynolds number for air case, they should be same. Okay? Now what's the formula for Reynolds number? Reynolds number is rho V L upon mu. It's rho V L upon mu. Should be like this, right? But this is for hydrogen case. This is for air case, okay? Now let's first talk about L. We know the characteristic length for hydrogen case. We know the characteristic length for air case. So this thing we know, L we know, right? Velocity. It is said that find out the air velocity in the wind tunnel. So this is actually we need to find. We need to make the two Reynolds numbers same. So we need to know what should be the velocity for the air case. Okay? But for the case of hydrogen, we know what's the velocity. Is it clear? Now we have the case of density and viscosity. Now here there is a small problem. Here we have a small problem. And the problem is that density varies with pressure. Okay, just a minute. Here, if you find out in the properties, I think we are given kinematic viscosity. Dynamic viscosity is not given, right? So instead of writing VL upon mu, I can write VL upon nu. VL upon nu. So it just now this term is there, and we need to find. Okay. Okay. Now there is one problem here. Okay. The problem is that in case of air, our pressure is 1 atmosphere. In case of hydrogen, our pressure is 2 atmosphere. But the problem is that in the tables, the values are all provided for 1 atmosphere, even for the hydrogen case. Even for the hydrogen case, the values are not provided for 2 atmosphere. So now we have to consider something, that what are the properties which depends upon pressure. Okay, look, wherever we have a change in the specific volume, that depends upon pressure. So density depends upon pressure. Okay, and since we know that this thing mu is equals to nu equals to mu upon rho, and it depends upon density. So if you change the pressure, density will change, and so nu will change, right? But other properties does not depend upon pressure. For example, thermal conductivity. If you change the pressure, thermal conductivity will not change. Cp, change the pressure, so thermal specific value of heat will not change. So other properties does not change Prandtl number, changes with temperature, but does not have effect on pressure. So if you change the pressure, Prandtl number will not change. If you change temperature, Prandtl number will change. Okay. So if you when we want to find out this kinematic viscosity, okay, so we have to consider the pressure. Now the pressures are the values for hydrogen and the value for air both are given at 1 atmosphere pressure. For the case of air, not a big issue because it is already at 1 atmosphere. So we can use directly the same value for the case of air, okay? But for the case of hydrogen, we cannot use directly the value from the appendix because the appendix value is for 1 atmosphere pressure and our hydrogen is not at 1 atmosphere, it is at 2 atmosphere. So we need to know what is the relationship between pressure and viscosity, okay? So now you know that nu is equals to mu upon rho, and since density will change with pressure, so nu will change with pressure, but mu does not change with pressure. It's only a function of temperature. This changes with pressure, okay? So basically we can write here that mu equals to nu into rho, right? Or rho can be written as specific volume, but it's the same symbol. So let me put a dash here for a specific volume, right? So now when I change the pressure, mu does not change. So, but for one pressure it was mu1 over volume 1. For other pressure it will be mu2 upon specific volume 2, right? It will be like that. Now you know that PV equals to RT. PV equals to RT. So that means P1 V1 equals to P2 V2. Okay, this V is basically specific volume, right? So that means we know that V2 is equals to or V2 upon V1. V2 upon V1 is equals to P1 upon P2, right? Now remember, we need to know the specific volume of hydrogen for 2 atmosphere, okay? The specific volume of hydrogen for 2 atmosphere will be equals to what? So now we have a relationship this, that's the viscosity over a specific volume, and we have a relationship between specific volume and pressure. Okay, so we can now substitute it. Okay, so that means V1 upon V2 is equals to V1 upon V2, but V1 upon V2 will be P2 upon P1. Okay, P2 upon V1. So now use this thing. So this is our viscosity, this is our pressure. Viscosity is linked with pressure by this relation. Is it clear? This derivation which I have done here is not done directly here. They directly put the formula here. Okay, that the viscosity 1 over viscosity 2 equals to P2 upon P1. Okay, they directly put it here, but this comes as a result of this derivation. If you don't put this derivation, it's okay. Okay, however, I have just done this derivation here to explain this thing. Okay, one might think that how come this formula came here. Okay, so now if we know viscosity at one condition and the pressure at that condition, we can find that if we change the pressure, what will be the viscosity. Okay, so we determined the new viscosity, and it will be what? The viscosity that you get from the table multiply by the pressure over which of the table divided by the pressure over which you are trying to find out. Okay, so it's actually divided by 2 in reality. Okay, so once you increase the pressure twice, so viscosity will become half. Okay, If when you increase the pressure twice, viscosity will become half. Because if you see here, the relationship is inverse. V1 upon V2 equals to P2 upon P1. You increase the pressure, decrease the kinematic viscosity. You decrease the kinematic viscosity, increase the pressure. Okay? So it's inverse. So now you have this thing. Is it clear? So if you have all these things, you can find out what is the velocity, what should be the velocity in the air tunnel. Is it clear? Don't forget what we were trying to do. We were trying to find out that what is the average heat transfer coefficient. For that, we need to make the two Nusselt numbers equal. For that, we need to make sure that the Prandtl numbers and the Reynolds numbers are same. Prandtl numbers we found by the properties, they are same, but Reynolds number will be same if the velocity is what we calculate. If after calculation we find out that if the velocity is 2.1 meter per second, then the two Reynolds number will also be same. Now once we are sure that the Reynolds number and Prandtl number are same, we can compare the two Nusselt numbers. Okay. Now what will be the two Nusselt numbers here? Okay. This will be the Nusselt number for hydrogen, HL upon K, and this will be the Nusselt number for air, HL upon K. We need to find, this is for hydrogen, this is for air. We need to find for the case of hydrogen. Is it clear? L is known, characteristic length for both the cases. Okay. K is also known for both the cases. If I know the H for this case, I will find the H for this case. Okay. Now here some information is given. Now read the information carefully. Okay. A geometrically similar strut of characteristic length 60 millimeter and parameter. So parameter is 150 millimeter. Okay. Is placed in a wind tunnel. Measurements reveal a surface temperature of Ts 30 degree when the heat loss per unit object length into the page. When the heat loss per unit object length into the page is 50 watt per meter. So basically what we are given is heat loss from this. Heat loss from the air case. Okay. So heat loss is what? Q is equals to H A delta T. Okay. What is our delta T? Delta T will be Ts minus T infinity. Okay. Ts minus T infinity. Ts for the air case is known. 30 degree. T infinity for the air case is known. Okay. H we want to find out. If we find this H, we will place this H here and we will find this H. Okay. Okay. Now the question is that what is the area? Area is the surface area. Surface area of heat transfer. Okay. So surface area is what? Surface area is this surface. Okay. So that will be the parameter multiplied by the length. That's the surface area. Parameter multiplied by the length. So I can write area here as P multiplied by L. Right? Now what's given here is heat loss per unit object length. And what's the unit? 50 watt per meter. So we are already given what is Q upon L. Is it clear? We are already given what is Q upon L. This Q dash is basically Q upon L. See the unit. Watt per meter. So this thing is known. Parameter is known. This is the parameter. Okay. So we will find H. Once we find this H, we substitute here. We will find this H, and that was the objective. Is it clear? So the question becomes a little complicated, but it was solvable. And he solved it using similarity. Don't need to perform expensive experiments. Use air, normal temperature air. No need to pressurize it. Use the regular pressure. Find out the H for the air case, then using the similarity, find out the H for the case of hydrogen case. Is it clear? Is there anything in the solution of the problem which is not clear? Please ask. Yes.
Can we solve without the, why will multiply P
Can we solve like this, I mean?
With L.
With L,
Yeah.
yes, if the length was given. But here the heat loss was given as per unit length.
So it's different.
Heat loss per unit length means if this is my wing, so per meter length of the wing, what is the loss given? If it is given that okay, heat loss is 50 watt and the length of the strut is 2 meters, then you put out whatever is the length, whatever the heat loss. Have to make sure what these units are very important. Sometimes the heat flux or the heat transfer units are very, sometimes they are given in watt per meter, sometimes watt per meter square, sometimes watt per meter cube, sometimes just watt. You have to look into the problem to see how it fits, where it fits.
How
In-
can we know from the equation of the, we need to use this Nestor number?
Sorry.
How can we know from the equation of the question we should use this method to solve the problem?
Okay.
And finally, maybe a route of question.
Okay, good. Good. Look, this is a question which clearly says that you have a case of hydrogen and somebody is proposing a case of air, and you had to perform similarity. Similarity is only done over dimensionless numbers. Similarity is only done over dimensionless numbers. So Reynolds number will be compared with Reynolds number. Velocity will never be compared with velocity. Prandtl number will be compared with Prandtl number. Temperature will never be compared with temperature. Okay, Nusselt number will be compared with Nusselt number. H will never be compared with another H. Okay, so now you know that you have to use these. Okay, is there anything that you do not understand? Good. This is a physical interpretation of Reynolds number. These two slides, consider them important for the short questions point of view. Physical interpretation of Reynolds number, this is a physical interpretation of Prandtl number. Okay, this you can skip. Anyways, we have another number, Stanton number. Stanton number is a ratio of Reynolds number over Nusselt number over Reynolds number into Prandtl number. Okay, but this number is not actually used much in heat and mass transfer. Anyways, now then we have the table of dimensionless numbers. Okay, this table is something it mentions all the dimensionless numbers that you have, that you will also be introduced in future. Okay, so but all of them are together here, and this table of dimensionless numbers is put in your book of formulas. Okay, so you have Biot number, you have mass transfer Biot number, your bond number, coefficient friction, Eckert number, Fourier number. This is the mass transfer Fourier number, friction factor. Then you have Grashof number, you will study in chapter number 9. You have Colborne number, you have Jacob number, study in chapter number 10. You have Lewis number, study in chapter number 14. You have Mach number you will not study at all here. Nusselt number is something you studied. Then you have Peclet number. I probably will study, either you have studied in fluid mechanics or you will not study. Okay, then you have Prandtl number, Reynolds number, Schmidt number, you will study in chapter number 8. Then you have Sherwood number, study in chapter number 8. You have Stanton number, it's not used much here. Then you have Weber number will also be not used here. Anyways, these are some of the numbers, okay, and they are placed here for your knowledge, and we will be using some of them in future as well. Anyways, this completes our chapter number 6, and from next class we will start inshallah chapter number 7. If you have any question, you can ask.